Okay, students, so now for the second part of the review, I'm going to jump right in on this. And what we'll begin to look at is just some inverse trig functions and evaluating some of these. And these things you just need to know your unit circle on. And the key thing is you want to know these things. You have to know these. I don't give this to you. So the ranges, particularly of these things. So if you have the inverse sine function, the range is from negative pi over 2 to pi over 2 in radians. So that means anytime you're doing an inverse sine, your answer has to fall within here. An inverse cosine is a little different. That is 0 to pi. So when you do an inverse cosine, make sure your answer falls within the range of 0 to pi. And then we'll look at the inverse tangent, and its range is from negative pi over 2 to pi over 2. All right, so these things are real important to know when you're doing these. The other thing that I see a lot from students is there's this thought that I have more than one answer. You only get one answer. There's only one defined answer when you do this. I mean, if you're going to do this on a calculator, two answers don't pop up, just one answer pops up, okay? So let's take a look at each of these then. So the idea is if you have an inverse cosine of some value, this really means the cosine of some angle theta is equal to negative square root of 2 over 2. And really this is an interpretation of the unit circle. So on a cosine, inverse cosine, you're from 0 to pi, so that means you're either in quadrant 1 or you're quadrant 2. You don't even pay any attention to what's going on down there. And we know the cosine is the x value on a unit circle, so that means just look at where x is negative root 2 over 2, and here's where it is. Okay, so that means the answer of this problem is just going to be 3 pi over 4. Okay, only one answer, and the inverse cosine answer has to fall from 0 to pi. Okay, so that's how you look at that. Okay, the next one, I'm going to erase some of these little marks I'm making as I go through this. The next thing is an inverse sine. So again, the meaning of this problem is the sine of theta is equal to square root of 3 over 2. All right, so a couple of things that you have to pay attention to. First of all, the range of an inverse sine is negative pi over 2 to pi over 2. What that means is you're either in quadrant 1 or you're in quadrant 4. Okay, so the thing is we also know that a sine is a y value. So what we do is we just look up where y is square root of 3 over 2. Okay, well that happens here, so that means the answer within that range is going to be pi over 3. Okay, so that's how that goes. That's how you figure that out. Real simple. But you have to know these ranges. It's real important, okay? All right, now the next thing is, let's look at a tangent now. So, and again, if I say arctangent, that means the same thing as inverse tangent. So this would just mean the tangent of some angle theta is equal to negative 1. Okay, the key thing on this is a tangent. You're either going to be from 0 to pi over 2 in quadrant 1, or you're going to be from negative pi over 2 to 0, you're going to be in quadrant 4. Okay, so you have to be in one of those two places. The other key thing that you have to pay attention to is a tangent is y over x. So you're trying to figure out where y over x is equal to negative 1. Okay, well, in here, the only place that it's going to happen is right here, because y is negative root 2 over 2, x is positive root 2 over 2. You divide those two quantities, you get negative 1. Now the key thing on this is the common mistake students make is they want to provide the answer 7 pi over 4. That's not right. We have to go clockwise to give an answer of negative pi over 4. See, that's a 45-degree reference angle right there. So you're going clockwise because you have to fall within that range If you're in quadrant 4, you have to give a negative angular answer then. So the answer to this problem would be negative pi over 4. Okay, not 7 pi over 4. That's wrong. Okay, and remember, I can't stress enough, there's only one answer to these problems. Just one answer, because this is a function. Okay, so now I'm going to erase this mess. And let's do this last one here. So the last one, arc sine, means the same thing as inverse sine. So this is just simply saying sine theta equals 0. Again, a sine is on a unit circle is a y value. So what you do is these things. An inverse sine has this range. That means that you're either going to be in quadrant 1, you could also be on an axis, or you're going to be down in quadrant 4. So you're going to be from pi over 2 all the way to negative pi over 2. So you don't even consider what's going on over there. Okay? All you got to do on this is look up where is y 0. The only place that happens is there, which happens at 0 radians. So that would be the solution of the problem. Okay? So the things that you have to know on this basically are, the definitions of the trig function, certainly. Cosine is the x value on a unit circle. Sine is the y value on a unit circle. Tangent's y over x. You have to know these ranges. Have to know those. And then you got to know your unit circle and how to interpret that. Okay? All right. So work on that and study that over. Next thing we're going to do is get into the identities. So with this one, and I'm going to move down this unit circle down here. Okay, so what we're going to look at now is the sum difference identities we learned. Okay, so you have to know the identities. So we're looking at the cosine of 255. Of course, 255 does not show up on the unit circle, but by the cosine sum identity, we can still do that. So the first thing that you want to do is you want to try to find two angles that are on the unit circle that either add or subtract to give 255. Okay, to me the logical way to do this, and there's more than one way to do this, just what comes to mind to me is 210 and 45. So we could change this problem to cosine of 210 plus 45 like that. Okay, now the identity goes like this. I'm just going to write this identity up here. For reference, if you have the cosine of two angles A plus B, it goes like this. It's cosine A times cosine B, then it has the opposite sign, minus, then it goes sine A times sine B. So I think of it as cosine, cosine, sine, sine, different sine. Cosine, cosine, sine, sine, different sine. And I kind of get into the rhythm and snap my fingers when I do that. Helps me remember that, okay, as crazy as it seems. All right, so let's plug this in. So what do? We do the cosine of 210 times the cosine of 45 minus the sine of 210 multiplied by the sine of 45. Now it's actually real easy to figure out. The cosine is the x value, so at 210, the x value is negative square root of 3 over 2. Okay, the cosine of 45, again, is the x value, so that is square root of 2 over 2. Okay, and then the sine is the y value, so the sine would be negative 1/2, and the sine of 45 is going to be square root of 2 over 2. Okay, so sine 210 is negative 1/2. Sine 45 is square root of 2 over 2. Be careful with your signs and everything. And then you multiply straight across. So this is going to be, when you have two radicals, both numbers are under a radical, you can multiply that together and get negative square root of 6 over 4. Over here, notice you're going to have a negative negative, so you're subtracting a negative. That's adding. Multiply that straight across, you're going to get that. Whoop, not that. 2 times 2 is not 2, teacher. It's 4. Okay, so what we'll have then is negative square root of 6 plus square root of 2 over 4. it's okay to write the answer that way. Probably the preferred way to write this is root 2 minus root 6 all over 4. Either one's okay though, all right? So that's it. Real simple to do that if you know the identity and how to use that. But again, the key thing is the unit circle. I don't give you a unit circle. You have to construct that. And I don't grade your unit circle. You just have to construct that at the beginning of your test if you want to, okay? Now we have a tangent identity. So I'm going to write down the tangent identity, tangent difference. So the tangent of A minus B is equal to tangent A minus tangent B. That follows, just the sign follows like that. And then the denominator is 1 plus the product of tangent A times tangent B. So we're going to be following this identity on here. So let's go ahead and get this plugged in. And then we'll have to use the unit circle to interpret this. Okay, so we follow the identity exactly. So the numerator is just going to be tangent x minus tangent pi. The denominator is going to be 1 plus tangent x times tangent pi. Okay, and we don't know what x is. It doesn't matter. What we're doing is we're simplifying this. All right, so what we need to do now is we need to figure out, well, what is the tangent of pi? Well, the tangent by definition is y over x. So if you go to pi, y is going to be 0, x is going to be negative 1, so you would have 0 over negative 1, which is equal to 0. So everywhere you see tangent of pi, you're just going to replace that with 0. Okay, so what we'll have is tangent of x minus nothing over 1 plus tangent of x times 0 like that. And then we just mathematically simplify that. The numerator is tangent x. The denominator is 1. So that gives tangent of x. Okay, so that's how you would utilize that identity. Okay, moving on to the next page, continuing to work with some trig identities here. Okay, let me bring this unit circle down here so I can get everything to work here. Okay, so let me bring this down just for reference as I move through this next problem. Okay, so now this one is going to be a sine sum identity. And for reference, let me write that down. The sine sum identity goes like this. Okay, so it goes sine, cosine, cosine, sine, same sign. So it's sine A times cosine B, same sign, and then backwards it's cosine A times sine B. Okay, so I think of it as sine, cosine, cosine, sine, same sign. Rhythmically, sine, cosine, cosine, sine, same sign. Okay, sticks in my mind, and maybe it will yours too. All right, so here's what we do. We look at two angles that can either add up or subtract to give 75. So the logical choice on here to me would be the 45 and 30. So let's work with that problem like this. So we're going to just change this to the sine of 45 degrees plus 30 degrees. Okay? And then when we move through this, to just put it in the identity, so it's going to be sine 45 times cosine 30, same sign, and I'll do it backwards, cosine 30 times sine 45. Okay? All right, so remember the sine, whoops, I think I have that backwards. I do. Okay, it goes like this. So now it's sine, cosine, and then cosine 45, and then sine 30. Okay, like that. You end up doing the sine of both angles and the cosine of both angles. That's how I caught my mistake. So we'll go through on that, and the sine is just the y value, so I'm going to highlight these y values of those two angles. The cosine is the x value, so I just do that. Okay, so that's where I get those numbers. So the sine of 45 is square root of 2 over 2. Cosine of 30 is square root of 3 over 2. And we have plus cosine of 45 is square root of 2 over 2, and the sine of 30 is 1/2. So the answer is going to look pretty similar to the problem I did on number 13, I think. So again, you get square root of 6 over 4 plus square root of 2 over 4. You got a common denominator already, so you can just write the answer as square root of 6 plus square root of 2 all over 4. Okay, students usually do really well with these identities as long as you know your unit circle. If you don't have your unit circle down, I mean, you're not going to do very well. So that's really, really important that you make sure you have that down. Okay, so the next thing I'm going to do, and I'm going to pause this for a second, and I'm going to bring up a list of identities, which will kind of help you to see what I'm doing, I think. Okay, so as I'm teaching this, I wanted to have just kind of a list of identities up here for reference. Okay, so what we're going to do on a couple of problems is just do some simplification. And there's more than one way to do this. One way you could do this problem is you could just FOIL it out if you wanted to. The other thing you could do, and I'm going to just look at it this way, I see a tangent popping up, and that makes me immediately think of the identity tangent theta is sine theta over cosine theta. So I'm going to change this like this and write my first step as cosine of beta times sine beta over cosine theta, or beta, plus 1, and then just leave the sine beta alone like this. Yeah, you're probably going to have to FOIL this in the next step, and you could do that at the beginning step, but the thing that I noticed on that is those cross out, so now what you're left with is you're just simply left with the sine of beta plus 1 multiplied by the sine of beta minus 1. Okay? Now what we're going to do is we're going to just multiply this out with the FOIL. So we do the first terms. Sine beta times sine beta is going to be sine squared beta. Then we do the outside term. Sine beta times negative 1 is negative sine beta. We do the inside terms. Positive 1 times sine beta is positive sine beta. And then we do the last terms, 1 times 1, negative 1 is negative 1. So notice what happens on this is those things cancel out, and we're left with sine squared beta minus 1. All right, now there is one more thing you can do on this. When you simplify, you're trying to get this down to one trig function, which I have, but you're also trying to get it to as few mathematical symbols as possible. So actually there's one more thing you can do. You can look at this identity right here, and what you can see on here is, remember, you can take these identities and you can rearrange them. So what we can do is if I move the cosine to the other side, I get sine squared theta is 1 minus cosine squared theta. So that means what I could do is I could replace the sine squared with 1 minus cosine squared. So this is just one way to do this. So I'm going to replace that with 1 minus cosine squared beta. Then I still have the minus 1. Well, what that's going to do is those are going to cancel out. You're going to be left with negative cosine squared beta as your simplified answer. And see, that just has one trig function, but it doesn't have the extra number. So that's a little bit more simplified than sine squared beta minus 1 is. You want to take that as far as you possibly can. Okay? All right. That's how I think through that. All right, let's look at the next one. And again, just kind of refer to some of these identities. All right, on this one, let's see. I think this one you could start out the same way with this. Okay, so let's just, on step 1, let's just change this to cosine x plus sine of x. But again, let's use the quotient identity, all right, and change the tangent x to sine x over cosine x. Okay, all right, and let's just kind of see where this leads us here. All right, now let's see. What we're going to do then is just, I'm going to bring down the cosine, and I'm going to put that over 1. And then if I multiply this straight across, I have sine times sine is sine squared x over cosine x like that. Now what I'm going to need to do is I'm going to probably need to get a common denominator and add these two things together. So the common denominator, excuse me, is going to be cosine x. So I'm going to multiply this fraction top and bottom by cosine x. And again, if you multiply the denominator by something, you have no choice but to multiply the numerator by the same thing to keep from changing the problem. So now what I'm going to have is if I multiply this straight across, cosine times cosine is cosine squared x over cosine x. Leave that alone. Don't cancel that or anything. Remember, we're trying to get a common denominator and combine this, and then this problem's going to work out kind of nicely. Okay, so we have the common denominator. You're now ready to write that in one fraction. The numerator is cosine squared x plus sine squared x. Okay, well, that should be this identity here, so we know that cosine squared x plus sine squared x is 1, so that means we get 1 over cosine x. Okay, and then we got one more thing we can do. We have 1 over cosine is equal to the secant, so the simplified answer on that is going to be the secant of x. So generally in these problems, you're trying to just use identities to simplify expressions down as far as you possibly can. So that's the idea, okay? All right, now the next thing I'm going to look at, I'm going to erase these highlights here, and we're going to do some proofs. Okay, so I'm going to move down the bottom, and we're going to prove or verify identities. Now, when you do this, the thing that I want to really stress is you've got to learn how to write your steps. Students usually have very little background for doing this kind of thing. So what I always want you to do is write one side down. Okay, so your steps always need to start this way. You can write the word proof or you can leave that off, doesn't really matter. But the key thing is write down the side that's the most complicated to you. And that would just kind of mean, well, which side has the most stuff? Okay, that's clearly a little bit more complicated than the right side. Then put an equal sign. Now, do not start these problems any other way. Just write a side, write an equal sign. And then you're going to go down your paper. You're not going to go right all over the place on here. Okay, if you need to do a little scratch work with your identities, you can do that at the side of your paper. And I'll talk about that as we go through this. So the first thing we need to do on this is we need to just think, okay, what are some useful identities? Well, we know a cosecant of x is 1 over sine. That might be useful. So let's go ahead and start that way. So change that to 1 over sine x. And it's going to look like we're making this more complicated. Okay, the other thing I see is a cotangent of x. Well, that might be nice to do cosine over sine, or you might do 1 over tangent. But I think what's better to get as many sines and cosines in here as we can. So I'm going to change that to cosine x over sine x. Couple of things now. I see students do this all the time. Drives me crazy. Drives teachers crazy. This is not valid. Okay, you got to have that x on there. Okay, I always tell students a sine without a angle is a sin. Okay, so you must have that angle x in there. Okay, don't be lazy. I think that's just being a little lazy, so you have to have that angle in there. Okay, now we move on to the next thing. Well, we got this cotangent. Let's do the same thing with that cotangent. Let's change that to a cosine x over sine x. And then we have the cosecant. Let's do the same thing with that. Let's change that to 1 over sine, like that. Okay, so that's a good starting point in the problem. There are other ways to do this, but this is a logical starting point. So it looks to me like what I have is I have complex fractions. Now, one thing that you could do on this is you could do this as division problem if you wanted to, or you could simply get rid of the sine x. So one way you could do this in your next step, I'm going to write this like this. So I'm just going to bring all this down. And the idea is you have a complex fraction. So you would like to multiply the numerator by sine x to cancel it out. then you have no choice but to do the same thing at the bottom. And see, that's going to cancel both of those things out, okay, which is nice. And then we're going to do the same thing here. We have cosine of x over sine of x. I'm just writing everything down. Okay, then what I'm going to do is multiply the numerator by sine x to get that to cancel out. And then I'm going to do the same thing at the bottom. Okay, so now if you write down what we're left with, well, what we're left with is a 1 here. We're left with a cosine x there. And then in the bottom, now we're left with a minus cosine x here and a 1 there. All right, now it's probably time to think about getting a common denominator. Okay, so let's go ahead and get a common denominator, which is cosine x. We need to make the denominators the same, so let's multiply this by cosine x over cosine x like this. Okay, all right, now what I'll have is it looks like I'm going to have, this is equal to 1 over cosine x minus cosine squared x all over cosine of x. Okay, like that. All right, put it together in one fraction. We have 1 minus cosine squared x over cosine x. Now remember, what we're trying to do is we're trying to prove that this is the tangent over the cosecant. So it looks like we're not getting there, but one more step will get us real close. The idea is when you see this thing popping up, cosine squared x, it should make you immediately think of this identity here. So this is stuff you don't have to show in your proof because you can do this in your head. So if I moved that cosine to the other side, then this would now say sine squared theta equals 1 minus cosine squared theta. So that means that the 1 minus cosine can just be changed to sine squared x. All right, now we're getting closer. Now, you got to get a tangent out of this, and you also got to get a cosecant out of this too. So what's going to happen is, what I see is I look at, if I have a sine over cosine, I have a tangent. Well, I do have a sine over cosine. Why don't we write this like this, say? Okay, so we'll have sine x over cosine x, and then we have that leftover sine x like that. All right, well, so what you can do from here then is this becomes tangent. Now, how about the sine? Well, a sine is 1 over cosine, or 1 over cosecant, so you could write this like this, multiply straight across, and then you've got what you're trying to prove. Okay, like that. Okay? There's a lot of work on that proof, but again, the idea is you're just using identities and just kind of working through it. Again, notice how I'm going straight down my paper. You want to keep putting those equal signs in there and just keep going until you get that side. So a good quality proof is always going to be you write down the left side or the most complicated side. You keep running through this procedure until the other side pops up. Okay, and that's the way that these things need to look. I see stuff when students do this on a test, a lot of times I see chaos, total chaos on papers. I can't grade chaos. I have to grade stuff that's really thoughtful, logical, and everything flows nice and smoothly from one side to the other. So that's what you're after, okay? And by the way, there's more than one way to do this. I could have written this proof in a little bit different way. Okay, so let's go to the next thing here. Okay, I'm going to do a few more of these things. So on the next thing here, again, you want to pick the side that's the most complicated to you. In this case, it looks like they're about equally complicated, but when I see this popping up, that makes me think of the sum difference identities. So what I'm going to do is when I write out this proof, I'm going to choose to just write down the left-hand side. I think it would be harder to go the other way. So we're going to start like that and write an equal sign. Again, that's the way you always want to start these problems. Always. Don't do anything different. Okay. So what we're going to do from here is we're going to write out these identities. So this identity right here, I'm going to write out that sign difference identity. So this goes like this. Sine of the first, cosine of the second, same sign, cosine of the first, sine of the second. Okay, that's what the sign difference identity is there. Okay, and then this one, well, we still have that minus sign, so you want to still bring down that minus sign. And I think it's real helpful to have this in a bracket. And then this is the same identity, so it goes sine of the first, cosine of the second, minus cosine of the first. Oh, I keep doing that wrong. Okay, so cosine of y times sine of x. Okay, so you want to start that way. You want to put those in your identity. Now what we're going to do is we're going to probably distribute that negative through there, see if there's any like terms that we can collect. So I'm just going to remove these brackets. So I've got sine x cosine y minus cosine x sine y. Be careful how you distribute. So that's minus sine y cosine x. And then minus a negative is adding a positive. So that would be plus cosine y sine x like that. Now what we want to do on this is we want to see is anything the same. So let's see, this is cosine x sine y. So those two things right there seem to be the same term. They're just in a backwards order. And then this is sine x cosine y. They also seem to be like terms. So yeah, these are like terms. So one of these plus one of these would be 2 sine x cosine y, and then these right here are like terms, so that's just negative 1 minus 1, so that's minus 2, and that will be cosine x sine y. And then notice that that matches what we were trying to prove anyway, so that's it. So that's a fairly straightforward proof. Everything works out nicely after you use your sign difference identities. All right, so that's how that works. Okay. All right, so let's look at this next one. Okay, so with this one, we've got, again, proof. Which side's more complicated? Well, this has got a fraction in it, so what I'm going to do on here is just write down the left side, sine negative x over cosine squared negative x like this. Now, what this makes me think of immediately is these odd-even identities. So we have the sine is an odd function, and the cosine's an even function, like we learned, so we can use those two identities. So what I'm going to start with, and again, you don't have to write the steps exactly this way. There's a little bit of leeway in what you can skip. So one thing I'm going to do on here is, okay, the sine of a negative angle is just negative sine of the angle. So we can do that. Now I would be careful with this square. I would go ahead and write this as cosine negative x, the whole thing squared. That's a pretty important way to write that. Now we know that the cosine of negative theta is just cosine theta. So we're going to be left with negative sine x over cosine of x, the whole thing squared. Okay, so I'm just utilizing those two identities. I'm, replacing equals for equals. All right, sine of negative x is negative sine x. Cosine of negative x is cosine x. Now what I'm going to do is I'm going to rewrite this as negative sine x over cosine squared x. Now it's a good idea to look at what we're trying to prove. We've got to have a tangent. Do you see a tangent in there? Hopefully you do. There's a sine over a cosine, and a sine over a cosine is a tangent. So let's split this up and write this as negative sine x over cosine x times 1 over cosine x. Okay, they mean exactly the same thing. So here it is now. Sine over cosine is tangent. And then what's 1 over cosine? 1 over cosine is secant. So now that's proved. Okay, very nice, elegant proof on here. This is about the level that you're tested over, kind of like medium. This is kind of like a medium level proof. Okay. All right, now let's look at 21 on the next page. And with this one, let's see what we got going on here. So let's start this way. To me, it's pretty obvious that the left-hand side is more complicated. So let's start by writing down the left-hand side. And then putting an equals sign. Okay, I can't stress enough. Do not start your proofs any other way. Okay, all right. Now we got to think about what we need to do here. It looks like, well, we got to get probably a common denominator. So a common denominator on this thing is just going to be both of these things multiplied together. I mean, each denominator has to have what the other one has. So let's start step one, kind of spread everything out here, and let's introduce our common denominator. So this needs to have a sign in it, so multiply this by sine theta over sine theta. Okay, bring down the plus sign, and then you have 1 plus cosine theta over sine theta. And then this needs to be multiplied by, well, what does this need? It needs a 1 plus cosine theta. So top and bottom get multiplied by 1 plus cosine theta. So the idea is the denominators have to be the same. Now they've both got a sine and they both got a 1 plus cosine. All right? So you need to write that step showing that you're getting a common denominator. Now you want to multiply this out. So sine times sine is sine squared. Now, what's real important to me on this is that you just leave this alone. Don't multiply that out because you're hoping things are going to cancel. So I'm just going to bring this down as 1 plus cosine theta, sine theta. And then if you go this way, well, we're probably going to need to multiply this out by FOIL. So first term, 1 times 1 is 1. Outside term, 1 times cosine theta. Inside term, cosine theta times 1 is cosine theta. And then the last term, cosine times cosine, is cosine squared theta. Okay, and then that's all going to be over this. I'm going to put it in the same order as this, although that doesn't make any difference. Okay, so we got that then. All right, now what we're ready to do is we're ready to combine this into one fraction. Okay, so we're going to have the denominator, 1 plus cosine theta times sine theta. All right, so if you look at these terms, it looks like we have sine squared theta plus cosine squared theta, and that means something. We know what that is. There's an identity for that. And then it looks like we have plus 1. And then these are like terms, so a cosine plus a cosine, 1 plus 1 would be 2 cosine of theta. And see, notice we're trying to prove that this is 2 cosecant theta. Well, the 2 has popped up now. So let's see what happens now. So the idea is we know that sine squared plus cosine squared is 1. So in the next step, we're going to replace that with 1. So we have 1 plus 1 plus 2 cosine theta all over 1 plus cosine theta over sine theta. Okay, like that. Okay, next step, we got like terms again. That's going to be 2 plus 2 cosine theta all over 1 plus cosine theta times sine theta. So what we're going to do, I'm going to move this over the side here. Now we're almost done with this. So it looks like, well, what are we going to do here? We got to, you can factor this. Remember, somehow something's got to cancel here. So you can take a 2 out of here. If you take a 2 out, that would leave you 1 because 2 times 1 is 2, plus cosine theta because 2 times cosine theta is 2 cosine theta. And then we're still all over 1 plus cosine theta, sine theta. Now, what happens? Absolutely, there we go. So now we get this. That's going to end up leaving me with 2 over sine theta. Okay. Well, from here, let me move this thing out of the way. Okay, well, you could actually just write the answer now, but technically what this is saying is 2 times 1 over sine theta. Okay, and we know that 1 over sine theta this is the cosecant theta. So you can see your identity right there. So then we get 2 times cosecant theta, and we have proved it. So we were trying to prove that this becomes this, and it does. So there's your proof. Nice flow. Step by step, equal signs, never losing those equal signs. Just doing things step by step until the other side pops out. That's the way your proofs need to look. It's real important. Okay, all right. So now we're going to transition to this last thing, a little bit more work with sum difference identities. So I'm going to move this over here. And I don't know if we really even need these identities for this particular problem. So the idea on this is, ultimately, what we're going to be doing is finding the value of the sine of alpha minus beta. So you can start the problem in a couple different ways. The first thing I'm going to do is I'm just going to write out that difference identity. Okay? Pause just for a second. Okay, so let's go ahead and get this one done. So what I would do is I would start off by just writing down this identity. So this is going to be equal to sine alpha times cosine beta, same sign, cosine alpha times sine beta. Now ultimately that's how we have to do this problem. We have to know what the sine alpha is, cosine beta, cosine alpha, and sine beta. Well, you've been given 2 clues in this problem. Clue number 1 is the sine of alpha is negative 4/5. So that means that thing right there is just going to become negative 4/5. And also that's in quad 3. So let's work with that a little bit. This will be kind of the second key step. So I'm going to write down what we were given. Sine alpha is negative 4/5, and the fact that we're in quadrant 3. Okay, well, the way I look at it is we know the sine is y over r. So that means in this problem what we have is we don't know what x is, but we do know y is negative 4, and we do know r is 5. Okay. Well, what we need to do on this is we just need to find x. You can find that by the Pythagorean theorem, or you might already know that that's 3. Okay, although you got to be careful about quadrant 3. So let's just go ahead and work this out. We'd have x squared plus y squared equals r squared. So that's x squared plus 16 equals 25. Subtract 16 from both sides. You can do that in your head if you want to. That's x squared equals 9. Then when you take the square root of both sides, you technically get x equals plus minus 3. So the thing is, you're in quadrant 3, and if you're in quadrant 3, x is a negative number, so that's going to be negative 3 like that. Okay, so the other thing that you have to do in this problem, see, is you have to know what the cosine of alpha is. So let's go ahead and do that right now. See, the cosine is x over r. So you would go negative 3 over 5. That's going to be what goes there then. Okay, so we're just trying to get all 4 of these things put together there. All right, then the next part of this problem is we have another given quantity. It says that the sine of beta is 12 over 13. So that's going to go there. And then we're in quadrant 2. So let's kind of put this together. So we're given sine beta equals 12 over 13, and we're in quadrant 2. Well, so the meaning of this then is we know again the sine is y over r. Okay, so what we're going to do here is we got to figure out the cosine of beta, so that means we got to know what x is. So we need to figure out x, but we do know y is 12, and we do know r is 13. Okay, so we could do the Pythagorean theorem unless you know the Pythagorean triple on this. So we'll have x squared plus y squared equals r squared. So that's x squared plus 144 equals 169. You can subtract 144 from both sides. So that would give x squared equals 25. Square root both sides, you get x equals plus minus square root of 25, which is 5. And we just need to know which it is. Well, okay, that's important. Well, we're in quad 2, so if you're in quadrant 2, x is negative and y is positive. So we're going to use the negative 5 like that. Okay, now going back to finish up the problem now, the cosine of beta is x over r, so that's now going to be negative 5 over 13. Okay, so now we're ready to put this all together, see. All right, so we just multiply straight across. This is going to be 20 over 65. This is going to be minus negative 36 over 65. Okay, you can add that together. That's 20 plus 36. So that's going to be 56 over 65 would be the final answer to that problem. This is a real good problem because it tests over lots of things. It tests your knowledge of the sum difference identities, quadrants, definitions of trig functions. There's a lot going on. It's a good exercise for that purpose. All right, so this last problem I'm going to do is this one. This one you're doing the cosine of 130 degrees times the cosine of 10 degrees plus the sine of 130 degrees times the sine of 10 degrees. Now, you can't use your calculator. I mean, these angles are not on the unit circle. But this has the structure of an identity. So we have these two identities. We have the cosine of a plus b is equal to cosine A, cosine B, minus sine A, sine B. We also have this identity, cosine of A minus B, is equal to cosine A, cosine B, plus sine A, sine B. So this follows this exactly. See, it's got the plus sign right there, but it's also got the cosine, cosine, sine, sine. So you're doing this in reverse. So in this problem, you could think of A is 130 and B is 10. So really, this just ends up being like this. So this is the same thing as the cosine of 130 degrees minus 10 degrees like this. So that's the cosine of 120 degrees. All right. Now, this is on the unit circle. Now, I'm not going to pull up my unit circle the way I do problems like this. And if you go into higher math like calculus and stuff, you don't always want to, take 5 or 10 minutes to complete the entire unit circle. All you got to know is, okay, we're in quadrant 2. 120 degrees is this point here. And this point on the unit circle goes like this. It's over a half, and it's up square root of 3 over 2. So that means the cosine is the x value of that. So that would go, the answer of the problem would then be negative 1/2. So one of the things you want to learn how to do, is, and you can do this on your test, I don't give you the unit circle, but as you need something, just kind of reason it out. Just reason out that one point. Okay, now that's kind of how that goes, is like that. Another thing that I kind of tell students sometimes, like this next point is negative root 2 over 2, root 2 over 2, and then this last point is negative root 3 over 2, 1/2. So it's going this way, 1, 2, 3. It's getting bigger this way. We're in the negative numbers, so it's 1, 2, 3 that way. And then the y values go 1, 2, 3 that way in a logical manner. All right, so that'll wrap us up, and I'll get this posted and look over this. Hopefully this will answer some of your questions and help you prepare for the exam. Good luck.